Okay, ladies and gentlemen, let's work through this. Example, find the inverse of the following function algebraically and graph it. Remember, when you're finding the inverse, you switch your x and y's. So I'm going to go ahead and say that this is y equals square root of x plus 2. I have to switch my x and y. So I'm going to get x equals the square root of y plus 2. In order to get rid of the square root, I take it to the second power on both sides, and I get x squared equals y plus 2. I'm going to pull my work up here, and I get x squared equals y plus 2. When you subtract 2 on both sides, you end up getting y equals x squared minus 2. Or if you put it back into function notation, f of x equals x squared minus 2. Either one of these is the correct answer. However, f of x is the most correct answer. When you're graphing this, remember how to graph a quadratic. You can either do your table or you can do the pattern. Doesn't matter. So here's x, y. Always start with our vertex. Our vertex is at -0, -2. And then when we're solving for it, we go up by 1, 2, 3. So if we're doing this, we have y equals, we plug 1 in, so 1 squared minus 2. You're going to get y equals 1 minus 2, which is you're going to get y equals -1. Okay, so if you are doing the pattern, however, you go up by 1, 3, and 5. So -1 plus 3 gives you positive 2. 2 plus 5 gives you 7. So graphing this, we start at 0, -2. And then we go back to our home base and we go to the right one, down 1, because that was what my next point was. And we graph. Remember, it lands on the other side as well because of our axis of symmetry. Okay, now looking at this after we just graph this is the inverse of function. So when we're taking our vertical line test, well, we hit it once here. Is there anywhere in our function where we're going to be able to hit it multiple times? No. So since the vertical line test passed, so that means we are a function. Okay, our next one, how to find the inverses of a table of values. How you find the inverse is you just switch the x and y columns. So use the following function, write a table, then find the inverse of the table. So remember when we were looking for writing our table, so here's x, y, and we know that really we're just adding 0 onto here because there's no vertical shift. Our vertex is -4, 0, so -4, 0. You always start with your vertex, and then you go up by 1 on your x's, so -3, -2, -1. And then our next one, we have our pattern. So 1, 3, 5. 0 plus 1 is 1. 1 plus 3 is 4. 4 plus 5 is 9. Okay, so this was just a review from last semester when we were graphing quadratics, and we're just kind of getting into the mode of now flipping your x and y's in order to find the inverses. So when I flip my x and y's, what seriously happens is everything on my x's now become my y's. So this is now our x, and we actually call this f inverse of x. So moving on through here, if we flip it, it was 0, 1, 4, 9, and -4, -3, -2, -1. So what I'm looking at here is explain whether the set of numbers represents a function or a relation, then create a table for the inverse and explain whether the inverse represents a function or relation. Okay, so we just did this problem up here, found the inverse of the table. Then the next problem that I just read off is going to be the exact same thing that we just did, but you're going to find the inverse. So looking back up at our first one, let's actually figure out, is this an inverse? So is the inverse a function? So is the inverse a function? So I know that's not on your notes, but I guess I want to kind of include that. Is the inverse a function? I would agree that it is a function because each x value maps to one y value. So yes, it is a function. All right. So sorry about going back there for a second, but I wanted to just identify if it was a function before we moved on to the next problem. So here's our next problem. Explain whether the set of numbers represents a function or relation, then create a table for the inverse and explain whether the inverse represents a function or relation. Okay, so looking at our first one, do we have a function or a relation? So I'm looking at my x's and I see 2 1s and they both map to a 4. So what this is telling me is it's a function. So it's a function. Even though there are 2 1s, there are 2 x equals 1, they have the same output of y equals 4. So this one is a function. So then our next one, if we're making the inverse of that guy, we're going to get f and then f inverse of x. And we just transfer, okay, we just switch the x and y's. So everything that was in the y column is now going to become in the x column. So 4, 5, 5, 4. And everything in the inverse column is what was in the x column. 1, 3, 2, 1. Looking here now, I have 2 inputs that are the same of x equals 5, but they're mapped to a 3 and to a 2. So this is incorrect. It's not a function. It's going to be a relation. So it's a relation. If you were thinking it's a function, that's incorrect. It is a relation because x equals 5 has 2 different outputs. X equals 5 has 2 different outputs, so it's a relation. Moving on to our last 2 problems. They're word problems. Every day, Miss Smith goes running. Day 1, she ran 5 miles. Day 2, she ran 3 miles. Day 3, she ran 6 miles. Does a scenario represent a function or relation? Okay, well, let's see here. Let's create a table. So days, miles, 1 day, 2 day, 3 days. First day she ran 5 miles. And then the second day she ran, day, miles. First day she ran 5 miles. Second day she ran 3 miles. And day 3 she ran 6 miles. Well, we only have 1 to 5, 2 to 3, 3 to 6. Our inputs do not repeat, so this is a function. We know it's a function because each input has exactly 1 output. Okay? All right.